Welcome to our lesson on derivatives of exponential functions. In this lesson, we will talk about mainly exponential functions, okay? Right, so an example is e to the power x is the simplest exponential function you would ever meet. Right, so when you are going to differentiate this, the good news is that when you differentiate e to the power x, the answer is e to the power x, okay? So the differential of e to the power x is the same e to the power x, right? So dy dx will give you the same thing. So based on this, we are going to generate a formula or a rule to help us to deal with all kinds of differential of exponential functions, okay? So let's start. So we will consider y is equal to e raised to the power f of x, all right? E raised to the power f of x. How do we differentiate this? So we would use chain rule, okay? So we use the idea of chain rule. But don't worry, in the initial stages, I would discover or talk about chain rule in details, then after which I'll show you a shortcut to perform the same operation without going through all this process. I mean, I like to lessen students' burden, okay? Right, so you let u be equal to the index, okay, to the power, all right? So u is equal to f of x, then you differentiate it. So du dx will be the f prime of x, okay? So that's the first differential of the function. Now, if you are saying that u is equal to f of x, then it means that y is actually e raised to the power u. Why? Because the f of x, you said that is u. No problem. But remember that when you differentiate e raised to the power x, you get e raised to the power x. So when you differentiate e raised to the power u, you will get e raised to the power u, okay? But remember that we are differentiating y with respect to u, so that will be dy du, okay? Keep this one in mind. Right, so now let's go and apply chain rule on it and see what we get. So by using the chain rule, okay, the chain rule says, so our dy dx, what do we have? We have dy du, okay, and then we have du dx. So that's, remember, dy will start and then dx will end it, okay? Keep this in mind, that the first will start and the last will also end it. What will be in between depends on the variable you are using. So assume I used k to be equal to f of x. This would have been dy dk, and this would have been dk dx. Okay, so the middle diagonal that depends on the variable that you use. All right, so now let's substitute these into the formula and see what we come with. Right, so we have this dy du is e raised to the power u, and then we know that du dx is the f prime of x. All right, so when we clean it up, this is what we get. Now what we did here was that this u, we said let u be equal to f of x, so we just put it back there and we are good to go. Okay, so what this actually means is that when you are given a function, okay, y is equal to e raised to the power f of x, just differentiate the power and multiply by the function itself, and you are done. Basically, that's what we are talking about. Okay, so now let's get the general formula. When you have y is equal to e raised to the power ax plus b, like I said, it means differentiate the power, okay? So when you differentiate the power, that's ax plus b will give you a, okay, times the function itself, and we're done, okay? So let's practice some examples. This is the first one that we have. Y is equal to e raised to the power 7x. Like I said, we would not necessarily go through all the process of using the chain rule, but if that is what you want, then please go with it. All right, so this is what you should do. You differentiate the power, okay, that will give you 7, then you multiply by the function, that's e raised to the power 7, and you clean it up, and then you have 7 e raised to the power x. Let's consider another example. Now we have y is equal to 2e raised to the power negative 4x. Okay, don't let this scare you. It's as simple as anything. Differentiate the power and that'll give you negative 4. Okay, so that'll come and multiply the 2 to give you negative 8. Right, so this is what I was talking about. You differentiate the power and that'll be negative 4, so it multiplies the 2, and then you clean it up. So what you have is negative 8 e raised to the power negative 4x. Okay, so always remember that after you differentiate the power, it multiplies by the function itself. So we differentiated the power, we got negative 4, then we multiply by the function itself. Okay, is that simple? Right, so now let's compound the problem a little bit. Now we have two functions that are multiplying. And you know, in our study of differentiation, when two functions are multiplying and we are to differentiate, that means we should employ the product rule. Okay, but I'm not going to use the long process. We are going to use the short process to differentiate this function. Right, so this is how you differentiate. You keep the first function, that's s squared, we keep it, and then we differentiate e raised to the power 2x. Right, but the differential of e raised to the power 2x is we will differentiate the index, the power, and that will give us what? 2. Okay, and then we will multiply by the function itself. All right, that's e raised to the power 2x, and that's what we have. Plus, now we keep e raised to the power 2x, and then we differentiate this function x squared, and that will give us 2x. Now we are basically done. This is algebra, so let's clean up. All right, this will multiply that, so we have 2x squared, and then we have e multiplying this, and this is what we have. You can leave it like this, or you might want to make it a little bit presentable. Why? Because you have 2x squared, you have 2x here, you have e raised to the power 2x, you have e raised to the power 2x. There are lots of common factors here. Okay, so let's pull 2x e raised to the power 2x out. All right, so when we put 2x e raised to the power 2x out, we are left with x plus 1. Okay, so this is good. Of course, you can leave it this way, but this is nice. Right, so we have a nice curve here. Now we are going to differentiate. Don't let this scare you. It works the same way. Okay, but this one, it is a big function. Okay, a big function, and then there are smaller functions within it. What am I saying? Right, so the big function is this whole thing raised to the power 6, right? But after that, we have the inner bracket. So when you see something like this, we use the chain rule. Okay, the chain rule. So first, we would differentiate the outer bracket, then we'll go inside the bracket and differentiate. Okay, so now let's do that. So when we are differentiating the outer bracket, that will be 6. We'll come and multiply here, right? Good, so that's 6, and then we go and subtract 1, so we have 5. Whatever is inside, you keep it. That's it. Times, then you go inside the bracket. Okay, you go inside the bracket to differentiate. Now, when you are differentiating e raised to the power 4x, that will be that will be you differentiating the power. Okay, and when you differentiate the power, you get 4. All right, then multiply by the function itself, and this is what you have. Then we come here. You differentiate the power, which is 3x plus 1. This is linear. Okay, 3x plus 1 is linear, and this is a constant. So when you differentiate a constant, that's 0. When you differentiate 3x, you have 3. Okay, so we bring the 3 down, then we multiply by the function itself. That's what we have. Okay, we are done.